In the deserts of northern Ethiopia, the ground is tearing itself apart slowly and steadily, in a way that most people living far from the region have never even heard about. Not metaphorically, literally. A crack running through the Afar region has been widening for 2 decades, and new research just revealed that the process is not unfolding the way scientists originally expected. What happens next, according to the geologists studying it, could reshape how an entire ocean eventually forms. The Afar region is not the only place along this broader rift system where the crust has visibly given way in dramatic fashion. In 2018, unusually heavy rainfall in Kenya's section of the Rift Valley widened existing fault lines into a massive crack that swallowed sections of road and farmland, drawing international attention at the time. Geologists were quick to clarify that the sudden appearance of that crack was not itself evidence of accelerated rifting, but rather a case of already existing underlying fault structures being exposed and enlarged by heavy rain eroding softer volcanic soil sitting above them. Even so, the event served as a highly visible public reminder that the entire rift system, not just the Afar region specifically, sits atop genuinely active, shifting geology capable of producing sudden, locally destructive surface effects. The story of this crack begins in September of 2005, when something extraordinary happened almost overnight. A fissure roughly 60 kilometers long, about 37 miles, tore open across the desert floor near the Dabahu volcano. It happened astonishingly fast, over the course of just a few days, triggered by magma forcing its way upward through the crust in what geologists call a dike intrusion, accompanied by intense swarms of earthquakes. Within months, additional crevices opened across the surrounding desert, and the ground itself sank by an estimated 100 meters in places. Scientists observing the event even documented magma rising. From the base of the newly formed rift, an almost unheard of opportunity to watch the earliest stages of ocean floor formation happening in real time on dry land, rather than hidden beneath miles of seawater as it normally would be. That 2005 event was not an isolated curiosity. It was a visible surface expression of something far larger and slower moving underneath, a process scientists have been tracking for decades called the East African Rift System. This is a vast network of fractures and valleys stretching thousands of kilometers from the Afar region in Ethiopia south through Kenya, Tanzania, and beyond. 3 tectonic plates meet directly beneath the Afar region, the Nubian plate, the Somali plate, and the Arabian plate, and all 3 are slowly pulling apart from each other, driven by heat rising from deep within the Earth's mantle. It is the same fundamental process that tore apart the ancient supercontinent and eventually created the Atlantic Ocean millions of years ago. Much of what scientists now understand about the pace and pattern of this rifting comes from a specific research technique that has transformed how geologists study remote, difficult-to-access terrain like the Afar region. Researchers, including doctoral students working out of universities in the United Kingdom, have used satellite radar technology to track extremely subtle ground movements across the rift zone from orbit, measuring displacement down to the scale of centimeters over time without needing constant physical access to a region that remains genuinely difficult and often dangerous to study directly on the ground. That technique is precisely what allowed scientists to confirm the rift's steady widening rate in the years following the dramatic 2005 event. And it remains the primary tool researchers rely on to monitor the broader rift system today, including the newly identified acceleration in the Turkana Rift section further south. Since that dramatic 2005 rifting event, satellite radar measurements have continued tracking the region closely, and the numbers are remarkably consistent. The rift continues widening by several centimeters every year, with some estimates putting the rate at nearly an inch annually. At that pace, scientists expect the Afar region will eventually connect with the Red Sea and the Gulf of Aden, flooding the rift and creating an entirely new ocean basin, one that would eventually separate the Horn of Africa from the rest of the continent. The timeline for that outcome is measured in millions of years, not centuries, so nobody alive today, or for a very long time afterward, will see the finished result. But the process itself is measurably, undeniably, already underway. This is where new research published earlier this year changes the picture in an important way. Scientists have long modeled the East African Rift System as unzipping in a predictable, sequential pattern, starting in the north near Afar, and progressively working its way south over time, like a zipper being pulled open one section at a time. New research examining the Turkana Rift, the stretch running through Kenya and southern Ethiopia, found that section of the rift system is approaching what geologists call a critical breakup stage, and it is doing so far more rapidly and in a different sequence than the standard north-to-south model predicted. Rather than the rift zipping open in the tidy, sequential order scientists had long assumed, a section sitting in the middle of that zipper appears to be approaching the verge of splitting open on its own timeline, independent of what is happening at either end. That finding matters because it suggests the underlying process driving continental rifting is more complex and less predictable than the standard model captured. A realization that has real implications for anyone trying to forecast where the next significant seismic or volcanic activity along this system might occur. If a middle section of the rift can independently approach breakup ahead of schedule, it raises real questions about how researchers should be modeling seismic and volcanic hazard across the entire rift system, rather than assuming risk simply propagates in one steady, predictable direction from north to south. The Afar region itself has continued producing visible reminders that this underlying process remains very much active, not just a historical curiosity from 2005. Between late September of 2024 and the end of March 2025, a prolonged earthquake sequence struck central Ethiopia, concentrated primarily in the Awash-Fentale area of the Afar region, between the Fentale and Dofan volcanoes, an area that had not previously drawn this level of sustained seismic attention. Over that roughly 6-month stretch, the region recorded 330 separate earthquakes, including 17 quakes above magnitude 4, just in the first several weeks of the sequence. The strongest tremor in the entire sequence reached magnitude 5.9, centered directly beneath Mount Fentale itself, producing violent intensity, shaking rated as severe on standard seismic intensity scales. The shaking was felt widely across Addisi, Ababa, southern Afar, southern Amhara, central Oromia, and parts of the Somali region, causing localized but serious damage and claiming at least 2 lives. This kind of prolonged earthquake swarm, clustered specifically around active volcanic centers within the rift, is exactly the pattern. Geologists expect to see as magma continues moving beneath the surface, testing weak points in the crust, and occasionally forcing its way upward in smaller versions of the dramatic dike intrusion that produced the 2005 Dabahu fissure. Scientists monitoring the region treat these earthquake swarms as a genuine early warning signal, since similar seismic activity preceded the 2005 rifting event before it fully manifested at the surface. The entire planet, drawing researchers from around the world despite the area's remoteness and challenging conditions. Erta Ele, one of the very few volcanoes on Earth known to maintain a persistent, long-lived lava lake, sits within the same broader rift system, offering researchers a rare, continuously observable window into the molten rock churning beneath the region. The nearby Danakil Depression, one of the hottest and lowest-lying places on the planet's surface, sits directly within the rift zone as well, its otherworldly, colorful mineral formations a direct visible consequence of the same underlying volcanic and tectonic forces responsible for the widening crack further north. So what actually triggers next, based on everything scientists currently understand about how this system behaves? The most immediate, recurring pattern is continued earthquake swarms clustered around the region's active volcanic centers, similar to the sequence recorded through the Fentale and Dofan area in 2024 and 2025, a pattern local seismologists now watch for closely whenever unusual tremor activity begins building in the region. These swarms represent magma actively testing the crust from below, and while most resolve without producing a dramatic surface event, they occasionally culminate in exactly the kind of sudden dike intrusion and fissure formation seen in 2005. Scientists cannot predict precisely which swarm will produce the next major surface rupture, but the pattern itself, a period of intensifying seismicity followed by a rapid, visible rifting event, is well documented within this specific region's geological behavior. Longer term, the newly identified acceleration in the Turkana rift section adds a genuinely new variable to how scientists think about hazard across the broader rift system, one that researchers say will require updated monitoring priorities across the region in the years ahead. If that middle section is truly approaching breakup ahead of the sequence predicted by the standard north to south model, it suggests other sections of the rift, previously assumed to be relatively quiet for a much longer stretch of time, may need to be reassessed for closer monitoring sooner than researchers had planned. For the roughly 2 million people living across the Afar region today, largely as pastoralists spread across a vast, sparsely populated landscape, this ongoing geological activity is simply an ever-present backdrop to daily life, one that occasionally produces genuine, serious hazards in the form of earthquake damage and shifting terrain, even as it simultaneously carries enormous scientific significance as a living laboratory for understanding how continents split apart and oceans are born. Local and national authorities continue monitoring seismic activity across the region closely, particularly around the active volcanic centers, where swarms have historically preceded larger events. There is also a broader scientific significance to this region that extends well beyond the immediate hazard picture, one that connects directly to humanity's own origin story. The Afar region and the wider East African Rift are closely tied to some of the most important fossil discoveries in human evolutionary history, since the shifting, exposed geological layers created by the same rifting process have repeatedly revealed ancient hominin remains that would otherwise remain buried and inaccessible. Continued rifting activity while representing an ongoing hazard for local communities, also continues actively exposing new geological and fossil material for researchers studying humanity's deep past. Before you go, if you want to stay updated on how this rifting process and the associated seismic activity continues developing, make sure you like this video and subscribe, because we will be tracking exactly what scientists uncover next. The crack running across the Afar region has already rewritten what scientists thought they understood about how continents split apart. It is still widening, still triggering earthquake swarms, and according to the latest research, who have spent 2 decades studying it closely. Watch how researchers describe this region in the coming months, not just whether another dramatic fissure event makes headlines. References to accelerated breakup timelines, unexpected rift segment behavior, or intensifying swarm activity near Fentale and Dabahu are the clearest sign that scientists are still actively working to understand a